Okay, number 59. Given the rational function f of x equals x cubed plus 3x squared minus x minus 3 over x squared minus 2x, find the slant asymptote. So what we need to do is we're going to use long division to sort of like pull out whatever we can from the numerator, and that will sort of represent that asymptote, and then that other portion that's left will end up going to like 0. Which creates sort of like a shape, maybe something kind of like this, where you might see a line go something maybe kind of like that. As it goes towards infinity, where it approaches it, doesn't really reach it. So here's what we're going to do for this question. We're going to have x cubed plus 3x squared minus x minus 3. We're going to divide this by x squared minus 2x. And it's really important to keep your powers in order. So like if there wasn't an x term here, you might say plus 0x. That way you know that there's a gap right here. So first thing that we want to do is look at this largest term, and we're going to divide it by this. So how many times can x squared go into x cubed? Well, it can go in x times, or it's like missing that x amount. So now we just multiply the x squared minus 2x by x. So we get x cubed minus 2x squared. Now we subtract these. So to do this, I like to put parentheses around it so that way I know that that negative goes through. So I know that these two here are going to cancel out, and then we'll have 3x squared minus negative 2x squared. So that's going to be 5x squared. So we have two negatives. And then we need to bring down this one. So we have minus x. So now I say, how many times can x squared go into 5x squared? Well, it can go in 5 times. So I say plus 5 here. Now I write, if I was to distribute that 5 into it, we'd get 5x squared minus 10x. So now we go ahead and draw this line. We say we're subtracting these. So 5x squared minus 5x squared, 0. Negative x minus a negative 10x, that gets us plus 9x. And then we bring down this minus 3. Now from here, notice the power of this is greater than the power of this. So we stop. And we say that our remainder is that part that we have left over. So we say that if we divide it, we get x plus 5 plus 9x minus 3 over x squared minus 2x. So now here, this here is the exact same thing as this here. We've just done a little bit of rearranging. And we can see that if we imagine x becoming really, really large, this term here will end up going towards 0 because we'll have some really large numbers squared, which kind of dictates the behavior of this. So as x becomes large, this is basically 0, and it's as if though we just had this. So that's why it's a slant asymptote. So from here, we just need to say that our slant asymptote is y equals that extra portion that we have, or what we were able to pull out from the numerator, basically. Okay, 60. Given the rational function, find the nonlinear asymptote, show all work. So we're going to do the same thing that we did in the last one, where we're going to use long division to pull stuff out until we're not able to pull anything else out, and that'll represent our slant asymptote. So to set this up, we're going to have x to the 4th plus 3x to the 3rd minus 5x squared plus 2x minus 6. We divide this by x squared plus 3x. So to start with, we say, okay, how many times can this term here go into this one? Or like what's missing between the two? So we can see that we can put an x squared into it. So now we take x squared and distribute it into x squared plus 3x. So that's going to be x to the 4th plus 3x cubed. So now we say, okay, let's subtract these two. So x to the 4th minus x to the 4th is going to be 0. 3x cubed minus 3x cubed is also going to be 0. Okay. So I guess we just continue on as normal. It doesn't matter that this is 0 because we just move on to that next term. So from here, we say we have minus 5x squared. And because this is only one term here, and I'm dividing, or I'm going to end up subtracting out 2 terms, I'm also going to go ahead and pull this one down as well. Plus 2x. So from here, we just say how many times can x squared go into this term? Well, it goes in 5 times. Or excuse me, not 5 times, minus 5 times. So now if we multiply this out, we get minus 5x squared minus 15x. So now take these and I subtract them. So negative 5x squared plus 5x squared is 0. And then we have 2x plus 15x. That's just going to be plus 17x. Then we're able to pull down this 6. So this is our remainder here. So if we were to write this out, we get that f of x equals x squared minus 5 plus 17x minus 6 divided by x squared plus 3x. So we can see that as x becomes really large, this term here ends up dictating the behavior of this, and it becomes like some number divided by a really, really big number, which is basically just 0, and we end up with just this as we go towards large numbers for x. So we say that our slant asymptote, and in this case, it's not technically like a slant asymptote because it's going to end up matching like a curve, is going to be this portion here. That's why we said it was non-linear asymptote, because this here is non-linear. It's a non-linear function. So we just need to say that y is going to equal what we were able to pull out, which was x squared minus 5. Okay, 61, starting with a, we have 3x squared plus x is less than 2 times x plus 2. So a good first step for these is to try and sort of factor it out and solve for the zeros of it. If we do a little bit of rearranging first, see that we have 3x squared plus x is less than 2 times x plus 2. So if we subtract the 2x plus 2 off to the opposite side, we get 3x squared plus x minus 2 times x plus 2 is less than 0. So now let's combine our like terms. We get 3x squared. So this will be a 1x plus a negative 2x. So that'll end up just being negative x. And then we'll have negative 2 times positive 2, so that's going to be minus 4. It's less than 0. So next, we need to figure out where does this equal 0. And then there's a couple ways we can approach this. So we want to factor it, ideally. Or we could use the quadratic equation. So a good way to factor these sorts of polynomials whenever you see like a coefficient out front is to try factoring by grouping. And the way that you do that is you're going to say, okay, let's take 3 times negative 4. So that's going to be negative 12. And then let's also write that we have a negative 1. So we need to think of two numbers that multiply to negative 12 and add to negative 1. So I can think of negative 4 and positive 3. So that'll work. So from here, we're going to take this 3x squared, we're going to take this negative x here. We're going to break it up into two different ones. So we'll have 3x squared plus 3, plus 3x, sorry, minus 4x minus 4. So we can see this here is the exact same thing as this. We've just broken this term up into two separate parts. We still say this is less than 0. So now we need to factor these, and we can see that both of these kind of have numbers in common. So we can see that this first one, we can factor out a 3x from it, and we'll have a x plus 1 left. You can see if we distributed this back in here, we get this. From this one, we get that. So, and then this next term, we can pull out a negative 4 from it. And whatever we pull out, we want the second term to match. So now we have minus 4, and then x plus 1. It's less than 0. You can see if you distributed this back in, we get both of these numbers. So now we say, okay, both of these two have an x plus 1 in common. So we're able to factor that out. So we end up with x plus 1 times 3x minus 4 is less than 0. So from here, we can see that we have our roots, x equals negative 1, and x equals 4/3. So our last step here is to make a number line, and we're going to plug in numbers to see what those intervals are that are less than 0. So we have something like this. And we're going to have negative 1 here. And then over here we have 4/3. So now let's choose a number that's less than negative 1. Let's say negative 2. Make it easy. So we go back to, we can start from right here maybe. Let's plug in negative 2. So if we plug in negative 2, f of negative 2, we're going to have 3 times 4, so that's going to be 12, plus 2, minus 4. So you can see that this is going to be a positive number. So what I'm going to do is put a plus here, which means that it is not less than 0. So we know that the interval from negative infinity to negative 1 does not work. Next, we try a number between negative 1 and 4/3, maybe 0, f of 0. We can see f of 0, we're going to have 0, minus 0, minus 4. So we end up with negative 4, which is less than 0. So I'm going to put a little negative sign here to know that we're in the negative region. And then lastly, we plug in a number greater than 4/3, say 2. If we plug in f of 2, we're going to have 3 times 4, so that's 12, minus 2, minus 4. So you can see that's going to end up being positive as well. So I'm going to put a plus here. You see that the only region on this number line where we're less than 0 is from negative 1 to 4/3. So the next step is to say, okay, we know that this is just less than. It's not less than or equal to. So that means that we don't include these points here. So on our number line, if we were to draw this graphically, we'd put an open circle here, then we'd want to highlight this section here. Okay, and then to write that in interval notation, we're going to say that we go from negative 1 to 4/3 is all in our solution set. Then we're done. Okay, 61b. This one's a little bit easier because it gives us the factored form to start with. So to start with, we're going to go ahead and say what the zeros of this function are. And because it's factored, that's really easy. All we have to do is set each one of these terms equal to 0. So we know that x equals, we get negative 2, negative 5, and 4. Okay. So we know that each one of these, if we plug in negative 2, it's going to work because that is equal to 0. If we plug in negative 5, our equation is good because this is equal to 0. If we plug in 4, this will all be equal to 0, which is equal to 0. So everything, we know that these numbers should all be included in our solution set somehow. But we want to find these intervals. The way that we're going to do that is the same way that we did last time. We're going to draw a number line here. And on it, I'm going to have negative 5. I'm going to put negative 2. I'm going to put 4. So next we need to see what happens in these intervals. So if I plugged in a number less than negative 5, let's say negative 6. So if I plug in negative 6, we don't even really have to do the math. We can just kind of check what happens to the signs. So if I plug in negative 6 here, for x plus 2, that's going to end up being a negative. So we know we would get a negative here, we would get a negative here, and we would get a negative here. So we would end up with 3 negatives. So that means that in this region here, no matter what we plug in, we should get a negative. Okay? And then we just repeat this process. So if I plugged in a number between negative 2 and negative 5, let's just say -3, we can see what happens. So -3 plus 2, that's going to be a negative number. -3 plus 5, that's going to be a positive number. And -3 minus 4, that's going to be a negative number. So we can see we're going to have 1 negative, 2 negatives, so that's going to be positive. So we should be positive in this interval, which is good because that means that we satisfy this condition. So next we choose a number between -2 and 4. Let's say 0. So if I plug in 0 here, we're going to have 2 times 5 times -4. So we can see that this is going to be a negative number. So this interval is negative, and then we choose a number greater than 4. Let's imagine maybe choosing 5. So this would be a positive number, and a positive number. So this interval here would be positive. So I'm doing the same thing that I did last time, where I'm just choosing numbers and plugging them in. But this time I'm not even really worried about what the numbers are. I'm just worried about what happens to the signs of each one of these, and then adding up how many negatives I get. Because I know if I get 2 negatives, our answer has to be positive. It doesn't matter what those 2 negative numbers are, the answer is going to be positive, and that's what we're worried about. So I can see that we want the intervals where we're greater than or equal to 0. Well, you can see that we have a closed circle here, closed circle here, closed circle here. It's going to be this region here, and then everything on this side here. So to write this in interval notation, we're going to use brackets because it's included. So we write brackets -5 to -2, and then we have a gap in our set. We have brackets 4 to infinity, and we always use parentheses around infinity. Okay, 62, starting with A, we're going to solve the rational inequality. So we have x plus 2 divided by x minus 3 is less than or equal to 0. So we need to find out where this equation either equals 0 or is undefined. You can see that it equals 0 whenever x equals -2, and we can see that whenever x is equal to 3, it's undefined. So I'm going to make a number line. I'm going to include these points. So we have -2, and we have +3. And notice 3 cannot be in our solution set because it's not equal to 3. But -2 could be, and this says equal to 0. So we know that -2 should be a part of our solution set. So from here, we're going to say, let's choose a number that's less than -2. Let's say -3. So if I plug in -3, I'm going to have -1 divided by -6. So I'm going to get a positive number. So I'm going to put a little plus here. And then if I choose a number between -2 and 3, let's say 0, I'm going to have 2 divided by -3. So that's going to be a negative number. If I choose a number greater than 3, like 4, this would be 6 divided by 1, so that's going to be a positive. So we can see that the only interval that we work is, or that our function is less than 0, is from -2 to 3. We also know that we can include -2, but we can't include 3. So I'm going to put a closed circle at -2 and an open at 3, and then I'm going to fill in that gap. Then to write this in interval notation, we use brackets around -2 because it works, and I'm going to use parentheses around 3 because it's not included. Okay, 62b, we have 2 over x minus 1 is greater than -4 over x. So our first step is to move everything to one side and get it equal to 0, or greater than 0, I suppose. So we're going to have 2 over x minus 1 plus 4 over x is greater than 0. So now here I want to get a common denominator between the two. So I'm going to multiply this one by x. And then I'm going to multiply this 4 over x by x minus 1. So from here, I can combine my fractions here and combine some like terms to get 6x minus 4 over x times x minus 1. And this is greater than 0. So from here, I need to find where is my equation undefined and where is it equal to 0. I can see it's equal to 0 whenever x equals 2/3. And I can see it's undefined whenever x is not equal, or whenever x is equal to 0 and 1. So if I plug in 0 and 1, my function is undefined, doesn't work. And whenever I plug in 2/3, I get 0, which also doesn't work. So from here, I'm going to make my number line. Oops. And on it, I'm going to include 0, I'm going to include 2/3, and I'm going to include 1. So let's start with a number less than 0. Let's imagine we plug in -1. If I plug in -1, I'm going to have -6 minus 4, so that's -10. And then in my denominator, I'm going to have -1 times -2. So in total, I get -10 divided by +2. So that means that I get a negative in this portion here. So next, I choose a number between 0 and 2/3. Let's say 1/2. So if I plug in 1/2, this will be 3 minus 4, so that's going to be -1. And then here, I would get 1/2 times -1/2. So notice here, this denominator is going to be a negative number, okay? And this here is going to be also a negative number. So because they're both negative, we're going to end up getting a positive answer here. And then let's say we choose a number between 2/3 and 1, 4/5 maybe. Or we could go with something like maybe 5/6 would be a good one to go with. So if I do 5/6 times 6, that's going to be 5. 5 minus 4 is 1. So in my top, I have a positive number. And in my denominator, I'm going to have 4/5 times -1/5. So I have a positive divided by a negative, which means that this portion here is going to be negative. Lastly, we need to check anything greater than 1. Let's say we plug in 2. This would be 12 minus 4. That's going to end up being 8, or positive. So we'd have a positive divided by, and then this would be 2 times 1, which is positive. So we get all positive numbers, which means that anything in this interval is going to be positive. So next we need to fill in the gaps here. Say, because we're looking for when is this greater than 0, we know that this portion here from 0 to 2/3 is good, and everything from 1 to infinity is good. We also know that x cannot equal 0, so I'm going to put open circle here, and x cannot equal 1, so I'm going to put open circle here. Then lastly, I know if x equals 2/3, our function equals 0. And if the function equals 0, it's not greater than 0, which means that it can't be included at 2/3. So next I just fill in here. I know that this portion here is good, and that this portion here is good. So next, I just need to write this in interval notation. I say we go 0 to 2/3, and I'm going to use parentheses because it's not included, then union 1 to infinity. I'm also going to use parentheses. And then that's it. Okay, 63, given g of x equals 7x minus 3, h of x equals x plus 3 over 7. Use composition of functions to determine if g of x and h of x are inverses. So what we need to do here is see if we plug in h of x into g, let's see if we get x. So to do this, we're going to have 7 times h of x, which is x plus 3, divided by 7, minus 3. So let's simplify this. So we can see that our 7s are going to cancel. We'll be left with x plus 3, minus 3. We're just left with x. So we know that this here was good. And we also, it's a good idea to check the opposite, just to make sure you didn't make a mistake. So we should see if we plug in g of x for h, if we end up with x, we're good. So we're going to have 7x minus 3, so that's g, plus 3 over 7. So now we can see here, these 3's are going to cancel out. This 7 will cancel with that, and we'll just be left with x. So this here is also good. So we can say, yes, they are inverses. Okay, 64. Starting with A, we're going to determine we're going to find the inverse functions and write an inverse function notation. So generally there's sort of like two different ideas or like approaches, but they're the exact same really. One of them is we say let's swap x and y. The other one is let's solve for x. So what I'm going to do is I'm going to take this equation that we have, f of x equals 2x minus 5 over 3, and I'm just going to like swap the two. So what I'm going to do is I'm going to say x equals 2 and times f inverse of x minus 5 over 3. So now I need to solve for f inverse. So to do this, I'm going to multiply by 3. I'm going to add 5. Then I'm going to divide by 2. So I found my inverse function. Super easy, right? And it's going to be the same thing for this next one, where what we'll have is f of x, equals fifth root of 2x plus 3. So I'm gonna take f of x, I'm gonna say that's x, I'm gonna take x and say that's my inverse function. So I'm gonna say x equals fifth root of 2 times f inverse of x plus 3. So now I have to solve for my inverse function. So I'm gonna take everything to the fifth power. X to the fifth equals 2 f inverse of x plus 3. So now I subtract 3, divide by 2, I get that f inverse of x. It's going to equal x to the fifth minus 3, divide by 2. And we're done.
Okay, looking at question 65 here. Sally wants to invest $35,000 of her retirement. She can invest at 4.8 simple interest for 20 years, or she can choose an option with 3.6% interest compounded continuously for 20 years. So first thing we want to know is the simple interest equation and the compounded continuously interest equation. So simple interest, that equation is going to be I is equal to PRT. And our compounding continuously equation, continuously, is P of T is equal to P initial e to the RT. Be careful with this compounding continuously because this P of T right here gives us what our value is at the end. So we're going to have to subtract that from our initial, or we're going to have to subtract our initial from that value. Start with our compounded simple. So start with simple. So our P is 35,000. Our R is 4.8%. So to put that in your equation, we need to have it in a decimal form. So we're going to divide it by 100, and it's going to be 0.048 times our T of 20 years. So plugging this now into our calculator, we're going to get 35,000 times 0.048 times 20. That's going to leave us with $33,600. Now looking at our compound rate, we know our principal value at time 20. We're going to have our initial of 35,000 times times e to the power of r, which gives us 3.6%, which we're going to convert to a decimal of 0.036, and then times our t, which is 20. So how much we have in our account after 20 years is what we just solved for here. So 35,000 times e to the power of 0.036 times 20 It's going to leave us with 71,905.16. But to know our interest, we'll have to take our interest is going to be equal to P of 20 minus our P at 0. Which in this case, our P of 20 is that 71905.16 minus our P at 0, which is our initial, which is at 35,000. So our interest for this one is going to be 36,905.16. So for this one, we want to know which one earns more total interest, which is going to be our compounding continuously, because this is greater than 33,600. So we know that that compounding continuously earns more interest. All right, now looking at question 66. Suppose that 12,500 is invested at 5.5 interest for 8 years. Determine the amount that would be in the account under the following compounding conditions. I'll start with A, compounded annually. First thing we need to know is our compounding equation that we want to use. So in this case, since we're compounding multiple times throughout the year, we want to use the equation A is equal to P1 plus R over N to the power of NT, where P is our initial principal, or initial amount, A is our final amount, R is our rate, N is our number of times compounded in a year, and then T is equal to time in years. So first off, looking at part A, we want to compound annually, which means we're compounding one time in 1 year. So let me spell annually right, annually. Our N is going to be equal to 1. So in this case, we know what the A value is equal to P, which is that 12,500, 1 plus our R, which is 5.5%. We want to convert that to a decimal by dividing by 100, so 0.055, so that our N was 1. Again, our N is 1, and our T is 8 years, so times 8. Now we can plug this in and start simplifying. So A is going to be 12,500 times 1 plus 0.055, so 1.055 to the power of 8. Just plugging that into our calculator, we'll have 12,500 times 1.055 power of 8, and we'll have value of 19,183.58. When we're dealing with money, we want to always round to 2 decimal places because that's how much cents we're allowed to have. Right? So now we want to look at part B, where we're compounding monthly. When we're compounding monthly, we're compounding once each month. There's 12 months in a year. So our N in this case is going to be equal to 12. So now we're going to say A is equal to our P in this case is 12,500. Then 1 plus our R is still that 0.055 over N is now 12, and then times 12 times 8, right? So simplify before we plug in the calculator. 12,500, then 0.055 over 12 is 0.00458 plus 1 is going to be 0.1000458 power of 8 times 12, which we know is going to be 696. So in this case, normally try and bring down all the values you can in your calculator. Keep the most decimal places to keep the most accurate answer. So you can plug this in. So 12,500 times plus over 12, what we have in that parentheses right there, so the power of 96. And we're going to have A is equal to 19,389.34. So now for 66C, we want to compound quarterly. So quarterly means we're compounding 4 times out of the year. Like a quarter is 1/4, right? So our n in this case is going to be 4. So now we're going to have A is equal to 12,500 times 1 plus our rate is 0.055 still, over n is now 4, the power of 4 times t, which is still 8. So now just simplifying a little bit before we plug it into our calculator all the way. 100, so 0.055 divided by 4 plus 1 leaves us with that 1 point, didn't mean to change the color there. 1.01375 to the power of 4 times 8, which is going to be 32. And then now just plugging this into our calculator, 12,500 times 1.01375 to the power of 32 is going to leave us with A is equal to 19,350.75. Okay, looking at question 67, a farmer depreciates a $120,000 tractor. He estimates the resale value V of T in $1,000 of the tractor 2 years after purchase is 80% of its value from the previous year. Therefore, the resale value can be approximated by V of T is equal to 120 times 0.8 to the power of T. So start off with part A here. I'm going to find the resale value 5 years after purchase, round to the nearest 1,000. So we're given the equation V of T is equal to 120, 0.8 to the power of T, right? So what part A is asking us to find is after 5 years. So we're going to do V of 5. So that means anywhere we see a T, we're going to plug in a 5. So we're going to have 120 times 0.8 to the power of 5. Plugging that into our calculator, we get V of 5 is equal to 39.32. That's in thousands of dollars. So rounding to the nearest nearest thousand means we're going to have $39,000, right? I don't know why I did that. So this is meaning that after 5 years, the resale value will be $39,000. Okay, looking at part B now. The farmer estimates the cost to run the tractor is $18 an hour in labor, $36 an hour in fuel, and 22 hours in overhead cost. Estimate the farmer's cost to run the tractor for the first year if he runs the tractor for a total of 800 hours. Include the hourly cost and depreciation. So first we want to find out what the hourly cost is. So remember, I had a function f of h, and that's going to be our hourly cost. So f of h, or f of x for some reason, f of h, we know it costs $18 an hour, so f plus 18 times h, $36 an hour, so we're going to add all these up, and then plus that 22h as well. So find out how much it costs an hour for just like the maintenance cost, stuff like that. So we're going to say f of 800 is going to be 18 times 800 plus 36 times 800 plus 22 times 800. So our f of 800 is going to be equal to 60,800. So now we need to find out how much it depreciates in that first year. So we can first go back to our resale equation, which we know is v of t is equal to 120 times 0.8 power of t. So after when t is 1 year, we can say v of 1 is equal to 120 times 0.8, which leaves us with 96,000, obviously, right? So about how much it actually depreciates, we have to do 120,000 minus our resale value to find out how much it depreciates. 96,000. That's going to leave us with 24,000. So to find out how much it cost the farmer to run the tractor for the first year, we're going to say, I'm going to say C for the cost is going to be f of h function plus that 24,000. So our cost, right, our cost is going to equal 6,800 plus 24,000. So our cost to run the machine in total is going to be $84,800. And this is the cost for to run the tractor during the first year.
Okay, so this next problem is asking us to convert the logarithmic equations to exponential form. Okay, so we have a little equation for that. So I can say log base A of B is equal to C. Then that also means A to the power of C is equal to B. So using this little equation exponential form we have, we can convert these things. So if we have log base 9 of 81 is equal to 2, then that 9 is going to become 9 right to the power of 2 is equal to 81, which we know that is true. So 9 squared equals 81. All right, so for this next one, we have log base A of capital M is equal to lowercase c. So this one's going to be A to the power of C is equal to uppercase M. So A to the C is equal to M. Okay, so for this next one, we're really just going backwards. So instead of having our log form, we have our exponential form. We want to make it a log form. So we have 2 to the 5th is equal to 32. For this log, we would have log base 2 of 32 is going to be equal to 5. Cool. And then our next one, we have C to the capital N is equal to D. And then if we convert that back, we're going to have log of C, log base C of D is equal to capital N. Okay, so for number 70, part A, it wants us to simplify these logs using basic properties. So we have the natural log of e to the y plus 4. On the inside, we can change this because of how exponentials work. We know that e to the y times e to the 4, we can separate it up like that, natural log. And then when we have things multiplied inside of a log, they're really two logs added together. So we can rewrite this as natural log of e to the y plus natural log of e to the 4. And then we know e and natural logs are opposites of each other, so they're going to cancel out. So then we're going to be left with y plus 4. This next part, part B, we have log base 2 of 2. And if we have a log, with the same base as what's inside of the log, those are going to cancel out and it's just going to become 1. So this is just equal to 1. So these cancel and we have just 1. Okay, so our next one we have 4 to the log base 4 of x squared. So kind of the same thing as the last one. If we have some number raised to the power of a log with the same base, those are also going to cancel out. So these cancel and we're left with x squared. The next one we have is log base 7 of 1. What we know about this is that any log with any base of 1, or base anything log of 1 is going to be 0. So if we have a 1 inside of our log, it's always going to be 0 regardless of the base. So that one is 0. Okay, so for this next one, it gives us this formula, pH is equal to negative log of H plus. Represents the pH of a liquid as a function of its concentration of its hydrogen ions, H+. Find the pH of the following round to the nearest tenth. So it's asking for the pH of bleach with an H+ of 2.0 times 10 to the negative 13. So what we're going to do is we're just going to plug 10.0, so pH, or 10.0, 2.0 times 10 to the negative 13, sorry guys, log, we're going to plug that in right here. So we're going to say 2.0 times 10 to the negative 13. We're going to plug that into our calculator, and when we do, we end up getting 12.7. And then we're just going to do the same thing for part B, except it's asking us for the pH of milk of magnesia, which we're going to plug in 4.1 times 10 to the negative 10, so log 4.1 times 10 to the negative 10. We're going to plug that into our calculator, and we end up getting our pH to be 9.4.